Hi everyone, welcome to the lecture 3 of the course of Convergence, Integration and Probability. And today we start talking about measure theory, and in particular we will introduce measurability and measures, and we will start seeing how this measure theory, how probability theory can fit into the framework of measure theory. Let me remind you that in the previous lectures we discussed some general notions of topology, in particular in metric and non-vector spaces, but I gave you the definition of general topology, and actually it would be nice to compare this definition to the definition of Sigma-algebra that we will see in a few minutes, and also that of measurability of functions to the characterization of continuity that we've seen in this theorem. So today we begin a series of lectures that is aimed at constructing a new kind of integral, an integral with respect to a measure. But first I would like to remind you the construction of the Riemann integral, so it will be very sketchy. I will do it very quickly, but yeah, I think it's interesting to have this in mind to compare to what we will do next. So for instance, let's say that we have a function like that. So that's the y-axis, that's the x-axis. And say we have a function f which is continuous, so that's my function f. And to compute the integral of f over, say, this interval here, say this is interval 0 to 1, what we do is that we look at rectangles which are below the curve of f. So I will discretize first my interval 0, 1 into smaller intervals, say like that, and I will consider the rectangles that are below. So I will try to put dot lines like this, etc. And I will look at the rectangles that are below the curve of f. So for instance, there is this one. Okay, that's the first rectangle. And then I look at the value of f here, and that gives me a new rectangle here. And then, well, this is another rectangle here that is below the curve of f, and so on. And so when I consider what I know how to do is to compute the area of these rectangles here in blue. And what I will do is approximate the integral of f. So the integral of f of x dx from 0 to 1, say, will be approximated by the sum of these rectangles. So I'm not saying exactly how these converge, when it converges, and so on, but that's roughly the idea of the Riemann integral. So there are several limitations to this. Let me mention a few ones. The first one, perhaps, is that this is really limited to integration. Okay, so this is limited to integration on the real line. So, of course, you can extend the Riemann integral to a d-dimensional space, a flat space actually, but this is not very natural, and this brings a lot of complications. And we'll see that it would be much more natural to do that, to work in RG with multiple integrals and so on within the framework of measure theory. So this is the first limitation, and also another one is that, well, you're also very limited to on the functions that you are able to integrate. So the functions you can integrate with the Riemann integral are very roughly the piecewise continuous functions. You can do slightly more than that, but not much more general than this. And in fact, you can have many examples in mind of functions which are non-continuous and which you would like to integrate, and in particular in probability, because like I said, we will put probability theory in the framework of measure theory. And there will be many cases where the function is not, that we want to integrate, is not continuous. So for instance, so limited to piecewise continuous functions And in probability theory, we'd like to integrate things like that. So for instance, the expectation that you might have encountered before. Well, if I want to integrate, for instance, if I want to compute, for instance, the expectation of some indicator function of an event A, well, this is actually, by definition, this is the probability of A. Okay, but this is also, by definition of the expectation, this is the integral over all possible events, all possible outcomes, I should say, capital omega, of 1 of A. So it's 1 if A happens on small omega, and 0 otherwise. And this is integrated against the measure. Here, this would be understood as a measure. So this is integrated against the measure P of omega. Okay, and here there are really almost no chance that this function here is continuous. I would like to integrate much more general functions. And you will see that, in fact, this integration with respect to measures, it brings significant improvements to what you've known before. And in particular, you're able to do like dominated convergence, interversion of limits and integrals. All these kind of things are very natural within the framework of measure theory. So all this will come almost as granted, while this was something quite obscure with Riemann integrals. Let's start with what we call a sigma-algebra. So this will be one of the fundamental definitions of this course. So pay attention to this definition. So a sigma-algebra, so let's say we start from a set E. Okay, E is any set. A sigma-algebra, calligraphic E here, is a family of subsets of E. Okay, just like a topology was a family of subsets of some set E or X. Here, a sigma-algebra is a family of subsets, and we will ask for three things, three axioms. The first one is that the empty set is in E, calligraphic E. The second one is that calligraphic E is closed under complement. That means that if A is in E, then its complement in E straight, is in calligraphic E. And the third point is that calligraphic E is closed under countable unions. That means, again, okay, being closed under something, you see the pattern here. Being closed under countable unions means that if AN is any family of elements of E, then the union of the ANs is in calligraphic E. Just a few things here, which are quite important. First, remember what countability, being countable means. So a set, let's say I. Okay, this is a reminder. I is countable if and only if, it's a definition. Actually, I is countable if there exists phi from I to n, which is a bijection. Okay, so this is countability, for example. Okay, let's say n, of course, is countable. Perhaps you know also that z is countable, q, okay, they are countable. And r is not countable. So we'll not give any more details here, but instead some consequences and perhaps some example of a sigma algebra, some simple example. So a sigma algebra, very simple. Let's say that E is made of three elements, A, B, and C. Okay, if I had just one or two elements, it would be too simple. So maybe let's start with three elements. These are sigma algebras. So for instance, you will have exercises in the example sheet where there are further examples, so you can practice to see if some families of subsets of E are sigma algebras or not. E, calligraphic E equals E and the empty set. This is a sigma algebra. let me give you another one. For instance, this one will be important. If I take all, okay, so all the subsets of E, okay, this is all the subsets of E, P of E. This is a sigma algebra, so that's a good exercise for you to check that these two families here are sigma algebras. Maybe a last one, let's say, okay, a third one here. For instance, this one. So notice that I always need, in my sigma algebra, I always need to have E and the empty set. So the empty set by assumption here, but if I take the complement of the empty set, okay, it's E minus the empty set, it's E itself, so E has to be in the sigma algebra. And perhaps I should add, for instance, A, singleton A, and A BC, for instance. Okay, so you see that this is somehow trivial sigma algebra. It's the smallest sigma algebra that you can ever construct, whatever E. This is probably the biggest because you take all subsets, okay, of E. And this one is intermediate, so sort of. Okay, you still have E in the empty set, and also you can check that everything we need is indeed in there. And you can construct other ones, of course, which are not this one or this one. Right. Now, first property of sigma algebras. The first one is that you've seen that by definition, a sigma algebra is closed under countable unions. Well, actually, it's also, you will see it closed under countable intersections. And it's also closed under difference, which means that if A and B are in E, then the intersection, so that was the first assertion. Actually, this can be made as a countable intersection, not only as a finite intersection. And the difference is here, so B minus A is in calligraphic E as well. So proof. So how do we prove that it's closed under countable intersection? So first point, let's AN, okay, be a family of sets which are in calligraphic E in the sigma algebra. Then the intersection of all ANs can be written like that. It's E. I will use the complementation. I will use these two properties. Okay, complementation here, and the fact that countable unions stay within the sigma algebra. So I will write this. This is E minus the intersections of the ANs. And actually, what's inside the brackets here is E minus the union for all N in capital N of E minus AN. Okay, this is something. This is set theory here. That's something that you can check yourself. And so this is equal to. Well, in fact, no. I don't need to say that this is equal to anything. Okay, I just need to notice that by definition of a sigma algebra, this thing here is in calligraphic E. It's in the sigma algebra. Okay, it's a stability by closeness by complementation. Then it's a union of elements of the sigma algebra here. It's a countable union that I have. So here this is again in calligraphic E. Now I have E minus an element of the calligraphic E. So all this is itself in calligraphic E. Okay, so the intersection of all ANs is still in the sigma algebra. Second point, that B minus A is equal to B intersected with E minus A. So this is in E. This, as we have seen, this by definition, this is in E as well. And we've just seen before that the sigma algebra is closed under an intersection. Okay, this is an intersection here, so all this is in E. So we have stability under countable intersection and difference. For a discrete set, such as the set of of natural numbers, it's quite natural and quite often we consider the sigma algebra of all the subsets of n, all the subsets of P of Z. So that's P of n or P of Z. But when it comes to the integral or to functions which are real valued, you might ask, what is a natural sigma algebra to put on R or on RG? Well, on R, P of R, so you can always say that P of R is a sigma algebra, and you could put P of R on R, but actually you will see that this is way too big for what we want to do. And what we want to do is, like I said, construct the integral. Actually, the problem is related to the measure. When we will talk about measures, if we want to have a measure that corresponds, for instance, if I take the measure of an interval, for instance, the interval 0, 1, and I would like this measure to be 1, which is a natural measure, it's a distance. I cannot construct a proper measure on P of R. P of R is too big. There are too many sets in P of R. This will not be an appropriate choice. So instead, we will rely on we will see here sigma algebras that are generated by subsets, which are more reasonable. They are not too big as subsets. So here is a definition, a first definition. If C is a family of subsets of E, then the intersection of all sigma algebras which contain C is a sigma algebra. And we call this sigma algebra the sigma algebra generated by C. Okay, so to put this clearly, this sigma of C here is the intersection of all the sigma algebras F, such that F is a sigma algebra, and C is included in F. Okay, so exercise for you. Prove that sigma of C is indeed a sigma algebra. Okay, and here this is rather some vocabulary rather than a new definition. But if you start from a topological set, okay, so T is the set of all open sets, then the Borel sigma algebra of ET, which we denote by B, this is calligraphic B here, B of T is a sigma algebra generated by all the open sets. So it's the smallest sigma algebra that contains all the open sets. So it's quite big, but it does not, as a matter of fact, in interesting cases such that R or RG, it does not contain all, it's strictly smaller, okay? B of RG is strictly smaller than all the subsets of RG, okay? And this will be crucial later. So note also here, so here I applied this definition to R or RG. Note the slight abuse of notation because here I did not write the topology of RG. I did not put the open set of RG, but RG itself. But here what I mean is that for the usual topology of RG, which is the one used by the Euclidean distance, for this topology here I consider the open set, and B of RG is sigma algebra generated by these open sets. Okay, so by complementation, observe also that B of T contains the closed sets, and actually contains much more sets which are neither closed or open. Let me define measurable functions. So measurable functions will be the functions, it will be the equivalent of the, say, the continuous functions for the Riemann integral, that the measurable functions will be the functions that we are able to integrate. So for that we need to define measurability. We need two sigma algebras and a function which goes from the first one to the second one. Okay, two measurable sets. And function f is measurable if f minus 1 of calligraphic f is included in E. So if I expand this expression a little bit, it reads like that. That means that for any b in the final sigma algebra, f minus 1 of b is an initial sigma algebra. So few remarks here. The first one is that perhaps I should remind you what this means. So f minus 1 of b, okay, this by definition, this is the set of all x's in E, such that f of x is in B. Okay, so that's for the definition. And also, it's nice to see that, and that's the part where I told you that it's nice to compare between topology and measurability and being continuous for a function and being measurable. If you remember well, we said that a function, okay, so recall function f from, say, okay, I will not call this E and F, I will call this X with some topology tau to some other space Y with topology tau prime, is continuous on X if, only if, f, so for any, let's say, for any u in tau prime, so for any open set in Y, f minus 1 of u is in tau. So if f minus 1 of u is an open set of X. Okay, that was the definition of continuity. So now you see how much it looks like measurability, except that here measurability is usually, for instance, for the Borel sigma algebras, the measurable set here, the sigma algebra, sorry, is much bigger. So in a sense, it's easier, okay, to be in calligraphic E. And proposition. So this one will be very, very useful. It's very practical. So if f is a sigma algebra that is generated by some family of sets, capital C, subsets of f, say, then f, if you want to check that a function is measurable, it's very convenient to have this criterion in mind. So f is measurable if and only if f minus 1 of C is included in calligraphic E. So that means that you don't have to check measurability on the whole sigma algebra f, but if you do this only on calligraphic C, that will be enough. So proof. Oops. Proof. Actually, this proof relies very much on the following lemma that I will call transport lemma. Which reads as follows. So let f be a function from two sets, okay, from E to F, sorry, and C be a family of subsets of capital A. F, family of subsets of capital F. Then f minus 1 of sigma of C is equal to sigma of f minus 1 of C. Right? So you can interpret the order of taking the pre-image and taking the smallest sigma algebra. It gives the same result. In particular, you see that this object is clear. It's by definition it's a sigma algebra, but it also tells you that this is a sigma algebra. And actually, this is part of the proof. So proof of this lemma, if you wish. So there is one inclusion which is easier than the other, which is that the term on the right-hand side here is included in this one. And to do that, observe that the pre-image of a sigma algebra is again a sigma algebra. Okay, so this is left as an exercise for you. But knowing that, it follows that f minus 1 of sigma of c is a sigma algebra. And observe also that f minus 1 of sigma of c contains f minus 1 of c. Okay, this is obvious. And as a consequence, the smallest, okay, we said that this is a sigma algebra. Well, the smallest sigma algebra that contains f minus 1 of c, well, is necessarily smaller than this one. It might be equal, but it has to be smaller. Okay, so this is a consequence. This is a sigma algebra by this the previous observation. So obviously, since sigma of f minus 1 of c is the intersection of all sigma algebras that contains f minus 1 of c, in particular, this one takes part of the intersection, and hence it's bigger than the intersection. Hence, f minus 1 of sigma of c contains sigma of f minus 1 of c. Okay, so that's for the first inclusion. And for the second one, it's a bit tricky, and I will give you the trick now. So let sigma, capital sigma, be this set of all elements of sigma of c, such that f minus 1 of a is in sigma of f minus 1 of c. So first, sigma is a sigma algebra. So you should check this. I'm not doing it here. Sigma is a sigma algebra, and it contains what? It contains, obviously, it contains c. It contains actually sigma of c, but it contains c. Okay, thus sigma of c is included in sigma, and also by definition, sigma is a subset of sigma of c. So this is included in sigma of c. So what we said is that sigma actually is equal to sigma of c. Well, look at the definition of capital sigma now. It's clear that f minus 1 of any element of sigma of c, okay, f minus 1 of sigma of any element of sigma of c now, because we've identified capital sigma, with sigma of c. So any element of sigma of c verifies f minus 1 of this element is in sigma of f minus 1 of c. So f minus 1 of sigma, or sigma of c, if you prefer, is included in sigma of f minus 1 of c. Right? This is exactly what this property says. And that's it for this lemma, actually. Okay, so that's the proof of this lemma. And now the proof of our result. So let's continue here. Well, for the first implication, okay, remember, it's an equivalence that we want to prove. So the fact that if f is measurable, then f minus 1 of c is in E, well, this is in calligraphic E, this is obvious because c is smaller than f, and we know that that f minus 1 of calligraphic f is included in E, so of course this is obvious. So that's by definition actually of c. And measurability if you want. Okay, and the converse implication, well, will be a consequence of the transport lemma. So f minus 1, what we assume is that f minus 1 of calligraphic C is included in calligraphic E, where this implies that sigma of f minus 1 of C is included in sigma of E. Okay? Sigma of E. So E is already a sigma algebra. So sigma of E is equal to E. And by the transport lemma, sigma of f minus 1 of C is f minus 1 of sigma of C. And sigma of C, what is sigma of C? Well, by definition, by assumption, say, okay, so this here is transport lemma. And by assumption, this is equal to f. Okay, assumption of the theorem, of the proposition. So we get that that f minus 1 of f is included in E. That is, f is measurable. Okay, and that concludes this lemma, the proof of this proposition. Sorry. Perfect. So as I told you, this will be a very interesting proposition when it comes to proving that an object is a function is measurable. We'll have the opportunity to use this result very soon. But let me first define Borel functions. Again, this is some vocabulary because there's no new concept in there. So a Borel function, when you have two topological spaces and you define a function f from the measurable sets which corresponds to these topologies, okay, remember, then f, which is measurable from E with the Borel sigma algebra here to f with its Borel sigma algebra there, is called a Borel function. Okay, so just some vocabulary. And then an interesting fact, which is that any continuous function defined from, for instance, Rn to Rp, here is a Borel function. So underlying here, what you should understand is that we are talking about the usual topology of Rn, which defines so the Borel sigma algebra on Rn, and that's the sigma algebra that we are using here. So maybe I can prove that very quickly. Yes. Okay, so proof of this fact. It's quite interesting to have this in mind. So yeah, you see, like I told you, in the end we'll be integrating most measurable functions, and the fact that all continuous functions are measurable, continuous in the sense that you are used to. So all continuous functions are measurable. That means that we will be able to integrate, at the very least, all the continuous functions, which is a very important point, actually. So proof. So this holds in much greater generalities than from Rn to Rp, actually. If you are Borel measurable, okay, if you are Borel function, whatever the space here, then you're measurable. If you're continuous from a topological space, then you're Borel measurable. But, okay, so let f be defined from E t to f t prime, so two topological spaces here, and let's assume that f is continuous. Okay, then that means that f minus 1 of t prime is included in T. Okay, so the pre-image of the open sets are open. Thus, sigma, and I will use the previous result, sigma of f minus 1 of t prime is included in sigma of t. Okay, I'm just using this relation here, sigma of t. And sigma of t, by definition, this is the Borel sigma algebra on t. And this, by the transport lemma, is f minus 1 of sigma of t prime, which is equal to f minus 1 of b of t prime. So you see that f minus 1 of b of t prime is included in b of t. Okay, so f is Borel measurable. So that's our proof using the transport lemma again. Another useful fact is that the composition of two measurable functions is measurable. So I will not do the proof, it just goes as for continuity, the composition of two continuous functions is continuous. Here it's reasonably the same. We will be, actually when we will construct integrals, that will be the integral for real valued functions. So as a matter of fact, as you will see next time, I will need to work in this particular space, r plus bar. Okay, and also you can understand why a little bit now is because we will use lim sup, and so the lim sup has to be defined in r plus bar. It's much more convenient to work in this space. So r plus bar is just the half line completed with plus infinity, and I will need, like I told you, I will work on Borel sigma algebras on R or on R bar. So I will need a topology, and the topology that we use here, I will not get too much into details, but you find what you need in this slide. It's called the order topology. Very roughly, but it's quite accurate actually, very roughly, it's the topology of open sets of R plus actually. So the usual open sets of R plus, to which if you want, you can add plus infinity to these open sets. Okay, so that's more or less what is said here in this sentence. And we will then, now that we will have we have a topology, we consider the Borel sigma algebra that is associated to these open sets. Okay, so that will be the Borel sigma algebra on R plus bar. So like I said, consider functions which are valued in R or in R plus bar with, now this will be the usual sigma algebra. We don't say anything, that means that B of R is chosen without ambiguity. Same here, B of R plus bar. 1a, so here are some properties of measurable functions. So first you see that 1a, the indicator function, which is defined here, so I recorded it for you. 1a of x is equal to 1 if x is in A, and 0 if x is not in A. Then 1a is measurable, this function, if and only if A is in E. The sum of two functions, so that's why in particular I need to work in R, because I will consider sum and product. The sum and product of two measurable functions is measurable, very useful then. And also if I take a sequence of measurable functions, then their supremum, their infimum, their lim sup, and their lim inf are measurable, right? And if it exists, their limit also is measurable. Well, in that case, if it exists, it's equal to this and this, so of course it's measurable. And if it exists also, the sum, okay, the series of function is measurable. So I will prove this. And the last point is that if f is measurable, then its absolute value is measurable as well. So let us prove this proposition by first the point 1. So proof. And I will prove the first implication. Okay, I will assume that 1a is measurable. So in that case, 1, notice that 1 is a Borel set because it's a complement of an open set. Thus, 1a minus 1 of this Borel set, well, since 1a is measurable, this has to be in calligraphic E in the sigma algebra, in the initial sigma algebra. Okay? And well, here you just have to observe that this is equal to A. So A is in calligraphic E, that's what I wanted to prove. Now for the converse implication, well, I will assume that A is a measurable set. Then I will evaluate the preimage by the indicator, the preimage of any Borel set of 1A. Then, so for B, a Borel set of R, 1A minus 1 of B is equal to, so I will consider several cases. The first case, let's say that 1 is in B and 0 is not in B. Then this is equal to A. Another case, so there will be 4 cases like that. Huh? So if 1 now is not in B and 0 is in B, so that would be E minus A. If let's say 1 is in B and 0 also is in B, then this will be the whole set E. And if none of them is in B, well, this is just the empty set. In any case, okay, whether it's A, E minus A, E, or the empty set, this is in calligraphic E. So 1A is measurable. Okay, so that's for the first point. Now the second is a bit more, is a bit more involved. So during the next lab actually, you'll see that exercise 3.3. You will see that you will prove, and that's very important, you will prove that P of R is generated by the set of the form minus infinity A, so those intervals, for A in R. Actually, the interval here can be closed in A, but here we will use this characterization. And then we will use the proposition that said that, in fact, to have a measurable mapping, it suffices to evaluate it on those sets and not on the complete sigma algebra. And if the preimage of these sets by the functions are in calligraphic E, well, then that means that the function is measurable. And okay, well, like I said, so I will write what I just said. Then it suffices to prove that f plus g minus 1 of the interval minus, so let's say, yeah, minus infinity A is in E for all A in R, to deduce that f plus g minus 1 of B of R is included in E. Okay, this is proposition 3.1.6. Okay, so that will be the content now to prove this relation here. Okay, so remember that f, this is a notation, but f plus g minus 1 of some Borel set of the form minus infinity A, okay, this is equal as the set of all x's in E, such that f of x plus g of x is in the set minus infinity A, so that means that it's smaller strictly than A. And I will write this set differently as the union. Okay, not also, okay, maybe just another notation before I go on, is that this sometimes, quite sometimes, it's written like that. It's f plus g smaller than A. It really means that it's a set of all x's such that f of x plus g of x is smaller than A. This is a very common notation that I will use again now. So I want to write this as a union and intersections and complement and this kind of operations, but they have to be countable. So this kind of operations, I want to decompose this set into smaller sets which I know are measurable. And what I know is that f and g separately are measurable. So what I will try to do is to write something like that. So the union for all r and s in R, say, first, where R plus S are smaller than A, so the union of these events, so F smaller than R, and, so and becomes an intersection, and G smaller than S. So you see, if there exist R and S such that the sum is smaller than A, then I can decompose f of x plus g of x. I can find actually r plus s, which is between f of x plus g of x and A, just in between, and such that f is smaller than r and g is smaller than s. That's what I'm writing here. Okay, so you can check this equality here between this set and this set. Usually you do that by double inclusion, this included in this, and conversely this included in this. And you verify that this is indeed the case. There's one issue here, that I'm looking here at R, a union over R, more or less, and R is not countable. So this union here is not countable. So I cannot really go on like this. And what I will do instead is say, okay, no, not R here, but what happens if I just put R and S, if I just choose R and S in Q, the set of rational numbers? Well, this is still an inequality because Q is dense in R. So I can actually replace R here by Q. And if I do that, now I know that Q is countable. And in fact, now I can finish my my proof by saying that, well, G is measurable, so this is in E. Okay. Remember, this set also, I can write it this way. This is G minus 1 of minus infinity S. This is in B of R. So this is in E. Okay, by assumption on G. So this is in E. For the same reason, this is in E. This is an intersection here, finite intersection, so this is in E. And now I have a countable union, so all this is in E. And now I have proven what I wanted, that is that this quantity here, the pre-image of this set, is in E. Okay, remember, that's exactly what I wanted to prove. Oops, sorry. Exactly what I wanted to prove here, which I have achieved here. Okay, so f plus g is measurable. Now the third point, which is the lim sup, the lim inf, and so on. So just try yourself with the same kind of argument. It's an exercise. And the fourth point, which I will not detail completely because it relies on the third one, but it would be important for later, let me introduce these notations. So the absolute value of f, I will write it as f plus, so a new function f plus, plus another function f minus, where f plus of x, for each x, f plus is a function which is equal to the maximum between f of x and 0. And similarly, f minus of x, so this is the positive part and the negative part of x. I will draw pictures later, but you can try to imagine what this is already. So this is the maximum between minus f of x and 0. Okay, the fact is that using the previous result, this is a measurable function, provided that you check that the constant function, which is equal to 0, is measurable. Which is again a good exercise for you. So f, the maximum, it's like the supremum of two functions. We've done it in third assertion, we've done it for countably many functions, so for two functions it works. So this is measurable. For the same reason, this is measurable. Minus f is a measurable function, so this is a measurable function. And now the sum of two measurable functions is again measurable. So the absolute value is measurable. And that concludes this proof. So we will have a look at a special class of measurable functions, which are called simple. So they are called simple for a reason, because they are quite simple. And indeed, these are functions which take only finitely many values, different values. Okay. And in fact, if you think a little bit, for functions from a measurable space E to R, so measurable, f, well, you can write it this way. Okay, it takes only finitely many values. They are denoted by alpha 1, alpha 2, etc. till alpha n. And in fact, what you observe is that ai here is just f minus 1 of alpha i. And since this is a Borel set, f is measurable, so ai itself is a measurable set. So it's in E. Right? I would like to emphasize on this function and to compare them to step functions. So perhaps you know that the Riemann integral is built upon step functions. Well, here the integral with respect to a measure will be constructed on simple functions. For instance, step functions are easier to draw because basically there are those functions which are piecewise constant, actually. So let me try this on the interval 0, 1. Okay, let's say this is 0, this is 1. And, well, there must exist a subdivision, so maybe small subintervals, big subintervals, small, etc. So I have a subintervals of 0, 1, in segment 0, 1. And my function, which is a step function, must look like this. So here it will take a constant value on this interval. Maybe here it will take another value. And here, between these 2 points, again, a different value. Maybe here another value. And then maybe it will go like this. Okay. And then like this, I don't know. Okay, okay, I've forgotten one, it's not important. And then, okay, here it has to be open. Okay, and here, maybe something like that. So this is a simple step function, and we can integrate it in the sense of the Riemann integral by saying, well, basically that the integral of this function is the sum of this rectangle here, plus this rectangle, plus this one, and this one, okay? The point of view is quite different when we look at simple functions. Actually, what we do is, instead of looking at dissection of the x-axis, we will do dissection of the y-axis. And here it goes. So let's say it's still 0, 1. Here it doesn't really matter. So that's saying that E is equal to 0, 1. And here I will choose finitely many values. So let's say this is alpha 1, alpha 2, alpha 3, and I will stop here. And what it's saying is that there is a measurable set. So let me try perhaps with a different color. And alpha 1 is the set of points in E for which f takes the values alpha 1. Look like this, perhaps. It can be a lot of different things, but can be quite complicated. Okay, but I will not make too complicated drawings, because otherwise you won't see my point. But let's say it can be very complicated where there are dots here, and then I will just go like this. And perhaps for alpha 2, so on this interval, say approximately, the function f takes the value alpha 1, so it cannot take the value alpha 2. But here, maybe between the points, okay, I will have something like that, mixed up with the blue dots, more or less, okay? And let's say that for alpha 3, the values are, maybe the function takes the value alpha 3 here, okay? So this is my function that I've drawn here, and you'll see that it can be much more complicated, because here, much more complicated than actually what I can draw. Because here on the left-hand side, you have only a finite number of subsegments of 0, 1, but here you can have many, actually I cannot count them, perhaps, for complicated functions. And what you see also, which is interesting, is that that's a simple function, but the set of simple functions contains the set of step functions. So when we say that with the Riemann integral we are able to integrate this, but with the new integrals that we will construct later we are able to construct this, well, the message also is that we will be able to integrate many more functions than before with the Riemann integral. And now a very important result when it comes later to constructing the integral is this one. So it says that any measurable mapping f, any measurable mapping which takes values in r plus bar. You see here, I forgot to mention that it's with the Borel Sigma-algebra of the open set that we've defined on this. So any such measurable mapping is the pointwise limit of an increasing sequence of non-negative simple functions. Okay, that means, more precisely, that for such f, there exists a sequence fn, okay, of functions. So for each n, fn, okay, is measurable from e to 0 infinity, and fn is smaller than fn plus 1, then, okay, there exists such a sequence such that, okay, maybe such that fn for any x in E, this is the notion of pointwise convergence that we've seen in lecture 2. For any x in E, fn of x converges to f of x, okay, as n goes to infinity. You see I use this arrow here that goes upward to mention the fact that fn is increasing. And the proof is in the lab, so you can have a look at exercise 3.5.